Okay, hello again. Welcome to the last in this spring semester Water Resources Research Center seminar series. This week we have Dr. Scot Izuka closing out our series talking about groundwater withdrawals and sustainable yield. He's been a hydrologist with the USGS Pacific Islands Water Science Center since 1989 and has conducted water resources studies in Hawaii, American Samoa, and Micronesia, plus forays into sedimentology, geomorphology, paleontology, geochronology, and stratigraphy. He is currently the project lead of the Hawaii Volcanic Aquifer Study, one of several USGS regional assessments of groundwater availability in the principal aquifers of the United States. Scott holds a BS in geology and geophysics from the University of Hawaii at Manoa, MS in geology from the University of Kansas, and a PhD in geology and geophysics from UH Manoa as well. So yeah, I think with that, I'll just go ahead and let Scott take it away.
Hey, thank you, April. Carrie and April. So I want to start by saying that a lot of this information, or some of this information, is preliminary. So just to let you know, it hasn't been peer reviewed yet and subject to change. Some of it hasn't been peer reviewed yet and is subject to change. So that's the caveat. But anyway, so let's get started. You know, as groundwater hydrologists, one of the questions that commonly gets asked of us is how much groundwater is available from Hawaii's aquifers? And more specifically, how much fresh water, because there's salt water in the aquifers too, is available from the aquifers for human use, because there are other organisms besides humans that rely on, for example, groundwater discharge to streams in the ocean. So, so in this talk, I would like to discuss some concepts that relate to groundwater availability and how the consequences of groundwater withdrawal relate to or limit groundwater availability, and then share with you some examples of how we try to quantify groundwater, these consequences of groundwater withdrawals. Oh yeah, I gotta do it this way. Okay, so all groundwater withdrawals have consequences. Yeah, even the smallest withdrawal from the smallest well is going to have some consequences. And in Hawaii, these consequences include water table decline, saltwater rise and encroachment, and reduction of groundwater discharge to springs, streams, and the ocean. It's really a mass balance problem, pretty simple mass balance problem. Under pre-development conditions, total amount of recharge that's inflowing into the groundwater system is balanced by natural outflow to streams, springs, and wetlands, and to the ocean. Inflows equal outflows. When that is upset by withdrawals from wells and from tunnels and other kinds of facilities, shafts and so forth, then that upsets the balance. The first thing that's going to happen is that the storage is going to shrink. And in Hawaii, where we have saltwater and freshwater, that includes water table decline and saltwater rise, so the freshwater will shrink. That will be the initial reaction, but eventually the change in storage is going to slow down and the system will transition to a new balance in which inflows equal outflows. And you can see that recharge hasn't changed, but the outflows now, some of it goes to wells and some of it, rest of it goes to streams, springs, and wetlands. So this total outflow has to equal the total inflow. In other words, whatever you take out of the wells is going to be balanced by an equal reduction in the groundwater discharge, natural groundwater discharge. So these things that are shown in orange here are the consequences of taking water out of the aquifer. You know, water table depression, reduced groundwater discharge to streams, springs, wetlands, and the ocean, and saltwater rise and encroachment. So how much groundwater is available? Go back to that question. And I know it says, it depends. The abstract says it depends. And I know everybody's going, oh my gosh, that's so frustrating to hear, but it does. It depends on the severity of the consequences a community is willing to accept, because like I said, any withdrawal has consequences. So what can we do about that? Well, the consequences that a community is willing to accept involve a lot of things that are kind of outside the physical hydrology that hydrologists are accustomed to dealing with. And those include things, these are things that managers have to deal with. It includes laws and statutes and rights, and it also includes human health and environmental health, and a lot of other things that we don't necessarily address in our hydrologic science. But if resource managers can decide on acceptable limits for the consequences, then scientists or hydrologists can quantify the consequences that are if managers can decide on the consequences, then scientists can estimate the availability of water that is within those consequences. Now, alternatively, the resource managers can propose a withdrawal rate that is desired, and then science can go back and find out what the consequences of that are, and then the resource managers can then in turn try to say, well, is that acceptable or not? Okay, so it's kind of like an iterative collaboration to kind of get to this goal. Well, the Hawaii Volcanic Aquifer Study is something that just about starting to wrap up. And just recently, like 2 days ago, we came up with our final report. And this final report addresses many of the things that I'm going to talk about today. And that includes the consequences of groundwater withdrawal and how that relates to groundwater availability. There are 2 previous reports too. This first report is a pretty good summary, I think, of the hydrogeologic knowledge up to the point of like when it was published, which is the mid, 20-teens, and has lots of references. And the second report is a description of the groundwater models which were used for the analysis in this study. Anyhow, they're all available online. And, okay, so one of the themes that run through that Hawaii Volcanic Aquifer Study is that the consequences of withdrawal differ by hydrogeologic setting. So in Hawaii, we identify these 4 principal hydrogeologic settings. There are some enigmatic ones that don't fit in here, and I'll get to that later. But anyway, the 4 primary ones are the freshwater lens, which is sometimes called the basal lens, dike-impounded groundwater, thickly saturated groundwater, where, and this is something that happens in eastern Kauai and parts of Maui. We'll talk about a little bit about what that is. And then perch groundwater. I think most people are familiar with at least number 1, number 2, and number 3. And I'll talk about the top 3, number 1, number 2, and number 4. I will talk about the top 3 in a second. I'll also talk about enigmatic occurrences. And in this set of islands, the one that comes to mind is the Schofield high-level groundwater, which doesn't really fit into these categories, and for which some things are known, but then a lot of things are not known. Anyway, I'll get to that. Okay, so freshwater lens. A freshwater lens, very familiar to many of us. It's usually in very high permeability lava flow aquifers, coastal aquifers, and in this setting, the freshwater exists as a lens-shaped body that sits on top of salt water that's permeating from the ocean. There's a brackish zone between them, transition zone between them. When you take when you take water from this setting, then it will cause the water table to go down, but also the salt water to rise. It will also cause reduction in discharge to the ocean. There are some cases where the freshwater lens is surrounded by this cap rock, which is sedimentary deposits that have been deposited at the coast, and they form a low permeability barrier. And that low permeability barrier retards the flow of fresh groundwater and causes the fresh water to get thicker. It's like traffic backing up on the freeway when there's an accident. So in this case, the freshwater lens is thicker, so that's good in the sense of this thinning of the freshwater lens. But when you take water from this setting, then again, you have the water table depression and saltwater rise. But then because some of this water, because of the cap rock, is discharging above sea level to streams, good example is a Pearl Harbor Springs, then withdrawing water from this system is going to take some of that water from the springs. The other another setting is deck impounded groundwater. Again, a lot of us are familiar with that. In this setting, we have volcanic dikes which form compartments in which groundwater accumulates to hundreds of feet above sea level. And the fresh water also extends pretty far down, probably to as far down as groundwater is still mobile. Under natural conditions, especially where there's erosion, under natural conditions, groundwater discharges to the surface from these compartments and supports stream flow. And near the coast, it will also support discharge to the ocean. When you take water from that, in this case, that can be done by a pumped well, like a vertical well, but also tunnels that bore into these dike compartments take water out. It will reduce groundwater discharge to streams and reduce groundwater discharge to the ocean. It will also reduce cause the water table to go down. As far as saltwater rise, that's probably not a big deal in this situation, except if you're at the coast, because in most of the dike compartments, the fresh water extends pretty far down the aquifer. Then there's the thickly saturated aquifers, which really occur in a few places, and in particular in eastern Kauai, where the rejuvenation stage volcanics have ponded in pre-existing depressions in the Kauai shield volcano, and they become thick and have just a general low permeability overall. And in that, because the permeabilities are low and a lot of water is flowing through these areas, the freshwater lens gets really thick. And it gets so thick that it actually impinges on the surface, and so it discharges a lot to streams and then less to the ocean. So you can imagine that if you take water from this system, then the consequences will include, again, water table depression, because if it's such a low permeability situation. It will also include reduction of stream discharge and reduction of discharge to the ocean. So the one enigmatic, that's what I call it. It's just we called it enigmatic because we didn't have a better name for it. But we lumped everything that we couldn't explain into this enigmatic category. But the one occurrence for that I'm going to talk about is a Schofield high-level water. In this case, it's high permeability lava flows, just like we have for the freshwater lenses, but the water levels are way higher than you would expect, a couple hundred, almost 300 feet above sea level, which is way higher than you would expect under this freshwater lens system. And drilling drilling data indicates that it's not perched, so it's probably saturated all the way down to sea level and probably way down below that. Many hydrologists envision some sort of a structure, geologic structure, low permeability structure that, for lack of a better term, has been called a groundwater dam, but that's causing this impoundment of groundwater or higher water level in this area. So for the Hawaii volcanic aquifer study, we created numerical models to assess the consequences of withdrawing water from these various hydrogeologic settings. We did 3 models, one for Kauai, Oahu, and Maui, using the mod flow SWI with the SWI package which is saltwater intrusion. So the model was capable of simulating stream flow reduction, reduction or discharge to streams to the ocean, as well as saltwater rise. And here's a cross-section of the Hawai model, for example. And this illustrates what the model simulates. You can see that for the freshwater lens systems, the freshwater thickness is pretty thin. For the thickly saturated aquifer, it's thicker. And for the dike-impounded groundwater, it's very thick. Actually, it goes down to the bottom of the model. And so does the Schofield high-level aquifer. So we calibrated the model to 2001 to 2010 conditions. And then we ran simulations, scenarios that we ran 2 past scenarios that looked backwards in history. And then when we compared the scenarios that we run for the past with the calibrated models, we can see what the impact that the 2001 to 2010 conditions have had on the aquifer thus far. Excuse me. We also ran some future scenarios and compared them to the calibrated model to study what these future hypothetical situations would, conditions would, how that would result when you compare them to the calibrated model. Okay, so in the first example I'm going to talk about is a comparison of the calibrated models to a no withdrawal scenario. And in the no withdrawal scenario, we just took the calibrated models, which had the pumping conditions for 2001 to 2010, and we just shut off all the pumping and the well and the tunnels to the free floating tunnels. So all withdrawals were shut down. And this, when you compare these two, we can see, we can study what the effect of the 2001 to 2010 pumping was. And here is a map that shows the water table altitude or change in the water table altitude caused by this pumping. And you can see that the biggest changes that were caused by the pumping seems to be, at least most obvious ones, are in the dike-impounded groundwater. And that's not surprising because the dike-impounded groundwater, you know, it's got these dikes in it. And so it's overall has a low permeability. And when you take water out of a low permeability aquifer, it's going to have a high drawdown. This is mostly effects from tunnels though. You can see that there's some effect also in the Waianae dike-impounded groundwater area, but withdrawals are less here. One thing you don't see that there's not a whole lot of water table decline relative, you know, to the dike-impounded groundwater in the freshwater lens, despite the fact that though there's a whole bunch of water being taken out of the Pearl Harbor and Honolulu areas. That doesn't mean there isn't any water table decline. There is, but compared to the decline in the dike-impounded areas, it's not as much. There's a little bit of color you can see in the Schofield aquifer too. What you do see in the freshwater lens is a rise in the interface, which is the freshwater saltwater boundary. So there, it's really apparent that the withdrawals, the 2001 to 2010 withdrawals have caused a big change in storage, you know, reduction in storage by lifting up the saltwater freshwater boundary. There's some changes in the dike-impounded groundwater here and there. These are actually where the saltwater is moving in, encroaching landward. But you can see that for most of the dike-impounded groundwater, it was not affected, at least in our simulations, by the withdrawal. This is a map showing the results of the model of simulated withdrawal on stream flow and springs. So you can see that one of the big impacts for the withdrawals of 2001 to 2010 withdrawals is, or the historical withdrawals, is reduction in stream-based flow in the dike impounded groundwater and the coalaus. There's some in the Waianae too, but withdrawals are much less here. Another big effect is in the Pearl Harbor Springs. This is the groundwater discharge to springs that are at the junction where the cap rock meets the basalt aquifer. Let's see. Okay, so another example, another backwards looking simulation that we ran is to run a recharge estimate that we had for 1870. And 1870 is when we had the first, 1879, I think, was the first modern well that was drilled in Hawaii. So we took recharge that was about that time and then combined it with the no withdrawal scenario. So this will compare changes that have happened in recharge between these two periods and withdrawals. Yeah, and what the result of that, of the changes in withdrawal and recharge. Okay, so most of the changes in recharge between these two periods has been, let me move to the next slide. Oh, no, I guess not. Well, most of the changes in the recharge between these two periods is because of agriculture. Agriculture either brought in water and irrigated fields, or they brought in ponds of reservoirs that leaked, and yeah, so it enhanced recharge in many places. But anyway, so this is an example of the result for Kauai, and this is change in water level. And the blue areas are where the water level increased, and the brown areas are where the water level decreased. And I don't have a map of this, but these blue areas correspond a lot, very closely with these spotty blue areas correspond with agricultural reservoirs. And then in general, there's also change in agriculture in this area. So the brown areas is where recharge decreased. And in many of these cases, especially near the near stream valleys, it was the change or the loss of taro irrigation. Okay. This is a map of the change in the freshwater saltwater boundary. And in this case, the most obvious one is around here in South Kauai, and that is where the Waita Reservoir is. And again, that's probably because leaks from the reservoir caused the freshwater lens, the bottom of the freshwater lens, to be pushed down. Okay, and another future analysis that we looked at was an increased withdrawal. So what would happen if we increased the withdrawal? So for this scenario, we raise the pumping rate at existing wells to their permitted rates. Now, for most of the wells, that meant an increase, because most wells currently pump at less than their permit rates. This is the permit rate. This is the rate that's on their permit from the Water Commission. And so you can see from this map, this is a map showing the increase, caused by this permit rate increase. And you can see that the increases are mostly in the central part of Oahu between the two mountain ranges. So it goes from Pearl Harbor to through Schofield and then to the North Shore. The bigger the dot, of course, the bigger the difference in increase in recharge, increase in withdrawal. Now, this is a map that shows change in water levels, and we can see that the result is pretty obvious in the Schofield area, where there was a large percentage of increase in withdrawals in this scenario. You can see that there's a tinge of color in the Pearl Harbor, Honolulu aquifer area, the freshwater lens area, a little bit less in the North Shore because the pumping increase was a little bit less. In the dike impounded groundwater area, there is a little bit, but it's really focused, and you can see that that color is pretty dark, so it's down here. So high intensity, but very localized changes in water levels. This is the map of the change in the saltwater freshwater boundary. And again, kind of similar to other maps that we've seen before, the freshwater lens, in the freshwater lens areas, that's where we see a change in the saltwater freshwater boundary. And this is a map showing the change in discharge to streams and springs. And again, we see a change in discharge to springs in the Pearl Harbor Springs area, which is a freshwater lens covered by caprock, and then a little bit in the dike and pond and groundwater area, but not as much as we saw previously because there was the increase in this scenario, so not as much as it was for the historical increase. There is a coastal change in coastal discharge too in the freshwater lens. So one of the things about the Schofield high-level groundwater area, which is right here, is that it is landlocked. So groundwater flows from this sector to adjacent sectors, which then reduces the amount of water that these areas get. And by increasing the withdrawal from this Schofield area, it reduced the amount of water that was flowing to these other lenses, which are freshwater lens areas, which are very important water supply areas for us. It also induced a little bit of inflow from the extra inflow from the dike and pond and groundwater. Okay, the last thing is we did a comparison of change in rainfall against the calibrated model. And this change in rainfall is based on the work that Oliver Tim was doing with statistical downscaling. And we use the 8.5 scenario with for mid-century. And this is a map of the change in recharge caused by that change in rainfall. And the warmer colors show a decrease in recharge. The bluer colors are an increase, but you can see that most of the island for Oahu has a decrease. I think island-wide, the decrease was about 15% in recharge. So what happened when we did that? Okay, so when we did that simulation, it indicated that a big impact could be seen in the dike and pond and groundwater in the Waianae area. And there's also, you can see some tinge of color in the dike and pond and groundwater of the Ko'olau and the Schofield high-level groundwater. This is, again, the saltwater freshwater boundary, and the saltwater freshwater boundary is encroaching landward, especially in the dike and pond and groundwater areas. We can see there's also a rise in the freshwater lens of Honolulu area, Pearl Harbor area. Okay, so what is the Hawaii Volcanic Aquifer study demonstrated to us that the primary consequences limiting availability of groundwater are going to differ for the different hydrogeologic settings. The freshwater lens setting, saltwater rise and encroachment, reduction of groundwater discharge to the ocean, and also to springs where there is caprock, is going to be the major limiting factor or consequence that might limit groundwater availability. In dike and ponded and other low permeability aquifers, including like the one on East Kauai, water level decline and reduction of discharge to streams and springs, it would be the primary limiting factors for groundwater availability. For upgradient aquifers like the Schofield aquifer, it's reduced flow to adjacent aquifers. We also, again, consequences, of course, depend on the magnitude of the withdrawals. The consequences change with changes in recharge caused by climate and land use changes. And the assessments that we did for this study are for a particular set of conditions that, a selected set of conditions, but the models can be used to simulate other kinds of conditions too, if so desired. Okay, so what happens if you have a situation where this kind of island-wide analysis is not precise enough. Like if you have an area where water resources are tightly shared amongst competing beneficial uses. In this case, you might need to dig a little bit deeper. And so what I'd like to do in the second half of this presentation is share with you some results that, or these two studies that we're doing in Windward Oahu that kind of approach this question. So these two studies, one of the studies is in the He'ia watershed, which is in cooperation with the Honolulu Board of Water Supply. The other one is in the Waihe'e Kahalu watershed, which is in cooperation. We're doing this study in cooperation with the Water Commission. Both of these watersheds are in impounded groundwater settings, which we talked about earlier. So they have a lot of connection between groundwater and surface water and stream flow. It's been known for quite a while that there's this connection between groundwater and surface water, even actually before and during the tunnel construction, that the substantial part of the stream flow comes from groundwater discharge, and that tunnel withdrawals affect stream flow. And then after they ran the tunnels for a while and they got to see the effects, they also realized that the effects of the tunnel, like the Haiku tunnel, didn't care about the topographic boundaries. It spread all the way to Kahalu stream. So the effects extend to streams other than the ones that are near the tunnels. So in both cases, in both watersheds, the management is trying to balance the needs of competing uses, competing beneficial uses, including drinking water for the community, agriculture and aquaculture, culture use of the stream water used for ecosystems and habitat, and traditional and customary practices, and recreation and aesthetics. So the Water Commission, to achieve this balance, is trying to plans to establish in-stream flow standards, and that limits the amount, or sets a limit on the minimum amount of water that needs to be maintained in the stream. Well, because there's a connection, like impounded groundwater, there's a strong connection between groundwater and surface water, then this constitutes a potential limit to the amount of groundwater that can be withdrawn from these watersheds. So the science objective, that's our objective for the study, is to try to quantify the impacts of the groundwater withdrawals in the streams. Well, one of the approaches to this is to look back at historical data. And fortunately for us, we have some gauges that have been in there for a long time, like this 109-year-old gauge on He'ia stream, which have been collecting data from prior to the wells and after the withdrawals. And so we can look at that. We're particularly looking at base flow. And again, base flow is the flow that persists in the stream during dry periods. So that would be this orange line here, whereas the gray peaks are from direct runoff from rainfall. And this base flow in these watersheds is from groundwater discharge. Okay, so one of the easiest ways to do it, quick way to do it, is to do this flow duration curve. Now, flow duration curve is simply a cumulative frequency curve with cumulative discharge on the vertical axis, and the percentage of time the discharge is equaled or exceeded on horizontal axis. And this is a probability scale, and this is in log scale. I know that's a lot to absorb, but basically, if you have a stream that does not have any groundwater discharge or any base flow, then this line would be pretty straight and go straight down into the horizontal axis at some point. Streams that have a lot of base flow will have this kind of dogleg in it. And that's the case for He'ia stream because of the groundwater, taking upon the groundwater. We divided these curves into 3 different periods. The first period shown in the black is the pre-development period before there was any tunnels or wells in there. And you can see where the base flow, which is shown by this part of the curve, this flatter part of the curve, is high. The red line is the first few decades after the tunnel was installed. So, and withdrawal from the tunnel was about 0.73 million gallons per day. And you can see that base flow was lower. About the 70s or 80s, I think, withdrawal from the tunnel was reduced because they put in another well. So that reduced the withdrawal from the tunnel. And you can see that base flow went back up to 1.12 million gallons per day. This is a map of the locations of the wells and the tunnel. Here's a curve for the Waihe'e stream, another example. In this case, there's 3 periods. This is the black line is a pre-development period. The red line is after they created the, they built the Waihe'e tunnel. And then the green line shows what happened after they drilled some wells farther up, but still upstream of the gauge. And you can see that you have a decrease in base flow caused by the tunnel or during the tunnel withdrawal period. And then another decrease in base flow when the tunnel and these wells were being used at the same time. Another analysis is a base flow time series analysis, where we use a computer program to look at the gauge records, and that computer program computes out or sifts out base flow from the full record. So the base flow is shown by this orange line, and the total flow is shown by the gray line. And it is cut off here because I wanted to expand the base flow part of the curve. And this curve is also truncated in 1972 because I wanted to expand this part of the period of the record. Okay, so what do we see here? Well, this is the Haiku tunnel. Again, is a Haiku. This is the Haiku tunnel construction period. This is the Haiku tunnel. The gauge is here. During the tunnel construction period, you can see that there's a bunch of peaks caused in the base flow. And this was caused by the actual tunnel construction. When they bored into the dike compartments, they dumped the water into He'ia stream. So it bumped up the base flow. Okay, so after that all was controlled, then we can see that there's a decline in base flow corresponding to this blue line, which is the withdrawal from the Haiku tunnel. After that, you can see that there is somewhat of a correspondence between, inverse correspondence between peaks in the withdrawal and troughs in the base flow. This is the same kind of graph, but for Ioleka'a stream, which is on the other side of this ridge here. But you can see that, again, the withdrawal from Haiku tunnel and even the construction of Haiku tunnel caused the base flow to decrease, and it's kind of stayed low. So again, the withdrawal didn't respect this topographic boundary, which is kind of expected. One of the things that we did was we compared the effect that Haiku tunnel had on these 2 gauges, or the stream flow measured at these 2 gauges. So in the pre-development period, the base flow at the He'ia stream was 2.24 million gallons per day, and it dropped to 0.84 million gallons per day right after the, in the 3 decades after the tunnel was put in. At Ioleka'a, pre-development was 0.88 million gallons per day, and that dropped to 0.31 million gallons per day. So, and here's the differences. And you can see that the decrease in base flow at He'ia was about maybe 3 times the decrease in Ioleka'a. And that's kind of understandable because of the proximity of that tunnel to this stream. This is, again, similar. It's a similar graph, time series graph to the one we saw a couple of slides ago. But in this case, I'm showing the entire record all the way to the 2022, I think, or 2021 of the HEIA gauge. And again, the blue line is the withdrawal from the Haiku tunnel. And for this analysis, we picked two periods, actually three periods. One period is the pre-development period, which is off the graph here. And then there's one period here where pumping is varying, but then it's not trending up or down. We picked another period, similar period, where it was not trending up and down, and tried to look at what the differences were. So going from period 1 to period 2, that's pre-development, to this first period when pumping was pretty high, or not pumping, but withdrawal from the tunnel was high. The withdrawal increase difference was 1.86 million gallons per day, and that caused a base flow, or it corresponds with a base flow decrease of 1.40 million gallons per day. But part of that might be due to rainfall, because rainfall also decreased by about 0.5 inches per day. Not a lot, but a little bit. Going from period 2 to period 3, there was a decrease in withdrawal. We talked about that earlier. Withdrawal, sorry, that should be decreased. Withdrawal decreased by 0.72 million gallons per day, but base flow increased. That should have been increased to 0.21 million gallons per day. But again, there's the problem with the some of that could be due to rainfall increase. Sorry, I got the labels backwards. So how do we get around this problem with rainfall, the effect of rainfall? Well, one of the ways, the way that we looked at is to do a double mass curve. A double mass curve is just, you take cumulative mass, it doesn't have to actually be mass, but any quantity that you cumulative over time, and compare it with another quantity that you think it would be related to. For example, rainfall and base flow. If the two are correlated and there are no changes, then it should be a straight line. But if you have a break in the slope like this, and that indicates that something changed in one of these quantities that is unrelated to variations in this other quantity. So this break in slope here indicates that there was a change in base flow that was not related to changes in rainfall, at least as measured at this gauge. So when you look at where these dots fall in history, you find that all these green dots are in the pre-development period before the tunnel was built. And then all the yellow dots are from the period after the tunnel was built. And before the tunnel was built, the average withdrawal was 3.33 cubic feet per second. And then, I'm sorry, before the tunnel was built, the average base flow was 3.33 cubic feet per second. And then that dropped to 1.35 cubic feet per second during this period. So there is a drop in base flow. And if we compare the drop in base flow to the amount of the tunnel withdrawal, and that's what's shown here, then that comes out to about 70% of the withdrawal is compensated by a decrease in stream flow or base flow. Another method of trying to quantify the effects of withdrawal is to do seepage runs. Seepage runs mostly are to see what the seepage patterns, groundwater patterns are in the stream. In particular, the seepage runs consist of measurements that are made at sites along the stream, selected sites along the stream during a dry period, usually all in one day. So because any changes from upstream site to the next downstream site can be attributed to groundwater exchange. So if it's an increase, then it's groundwater discharge. If it's a decrease, then it's groundwater seepage. We did seepage runs in four different days that span dry season and wet seasons. And this graph shows the discharge that we measured at each one of these, on each one of these seepage runs, plotted along distance along the stream channel. So the steeper the slope, the bigger the gain per unit length of stream channel. And you can see that, oh, by the way, the solid lines are for He'ia stream. These dotted lines are for Ioleka'a stream. And you can see that for He'ia stream, it continues to gain almost for its entire length, except for just the very end here. We'll talk about that in a second. Ioleka'a stream is pretty flat, but because it was flowing, just because it was flowing during a dry period indicates that this is groundwater discharge. One of the things that is really interesting about this is the location of the He'ia gauge, the gauge that we've been using for all the analyses that I talked previously about. And that is here. And you can see that that's like here. So you can see that He'ia stream gains a whole bunch of water that's not being measured at this gauge. So it would be really good if we could have another gauge that for future monitoring that captures some of this water. And of course, I won't ask a question if I don't have an answer. We are cooperating with the Honolulu water supply, and a new gauge has been installed right at the confluence, just below the confluence of Ioleka'a stream and He'ia stream. We've also been running 2 temporary gauges during the period of this study, which we will analyze in the future. Okay, another way to approach this is to use the groundwater model that we use for the Hawaii volcanic aquifer study. Since the model was already there, there's limitations. One of it is it's kind of a coarse model. Not all the streams are simulated, and the dikes, not individual dikes, are not simulated. But then it's still, I mean, the model already existed, so it was, you know, easy to use, and it was kind of a no-brainer to try it. But anyway, okay, so this is one of the things that we could do was simulate what would happen if we shut down the withdrawal from Haiku Tunnel. And this map shows the results of that. The colors indicate the increase in base flow at these streams caused by the shutdown of 0.6 million gallons per day from Haiku Tunnel. And you can see that by shutting this tunnel down, streams as far as Kahalu stream and as far south as Kuo stream, and actually some into the leeward side of Oahu, at least by the model, is indicating that base flow will increase from that shutdown. Here's another simulation. This one is a shutdown for a bigger withdrawal, and this is from Hawaii Tunnel 4.35, and of course it affects a bigger area. You know, I'm running out of time, but let's see. One of the things that we can do with the data from the model is to compare the effect on streams with the changes in the withdrawal rate. So because this is we've shut down the well. So in this case, we shut down Haiku Tunnel by 0.6. And then we saw a change in base flow of 0.12 million gallons per day in the He'ia watershed. That's only 20% of the change. That means that 80% of the change is happening elsewhere. It's happening in other streams, maybe streams as Kahalu or Ku'o, and changing in base flows to the ocean. And we did other combinations, Haiku well, Haiku Tunnel, and well, but they're all about that. It looks like a change about 20 to 26% of the change is accounted for by streams in the watershed. Okay, good. Back to summary. So again, going back to the whole question about sustainable yield. So I'm going to actually start with the second bullet point. Sustainable yield is not a single number. It's going to vary on what consequences you're willing to accept, and it will change with climate and land use changes, which change recharge. And groundwater availability is limited by the consequences of withdrawal, which differ among the hydrogeologic settings. The expanded studies can, like the ones that we did in He'ia and Waihe'e, can provide detail where management decisions are a little bit more critical. So, for example, in Windwater Oahu, we found that we could quantify, we could use historical data to quantify the effects of historical changes in base flow caused by historical changes in withdrawal. We could estimate what might happen if we shut down the tunnels using the groundwater models. And we also are able to quantify how streams, how the stream discharge is distributed, groundwater discharge to streams is distributed along the stream channel to help us improve monitoring. And just to reiterate, I think the key here is collaboration between management and science, and even iterative collaboration to reach a balance between groundwater withdrawal and the need to limit the consequences. So with that, I am open to questions. I would like to first I'd like to acknowledge the sources of funding: the USGS Water Availability and Use Science Program, the Honolulu Board of Water Supply, and Water Commission funded these studies. I had a whole bunch of people working with me on these studies, and also a lot of people in the community who have helped with access to property and so forth. So with that, I can answer questions.
Great. Thank you so much, Scott, for that really excellent talk. So I'll go straight into the questions, and we already have one in the Q&A section, so I'll go ahead and read that. This is from Ali Toulier. Thank you for this very fascinating presentation. The questions are: old reports from the USGS mentioned the Honolulu Artesian Basin. Seems this Artesian Basin is not mentioned anymore in current reports. Does it mean that artesianism does not occur anymore in Honolulu? And then any groundwater simulations of the basal aquifer regarding this hydrodynamic singularity?
Oh, I think it may be just a change of terminology, that it's not referred to as the Artesian Basin anymore. The concepts of freshwater, overlying saltwater with the cap rock are still the same. And whether I know Stearns called it the Great Artesian Basins of Honolulu, but the terms may not be used so much anymore because we found other terms to use it. I'm not sure if that's answering your question, but I think that's why the artesian part is not there now. It's not anything has changed. The terminology has changed, except for the terminology.
Okay. If anyone else has a question, again, feel free to enter it into the chat, or you can use the raise hand reaction. And I'll also enable people to turn their cameras on. First question in the chat is from Stephen Howell. Says the model appears to be an equilibrium model. What kinds of timescales are involved?
You are right. It's a steady state model. And I did kind of gloss over that. Because it's a steady state model, there is no measure of time or how much time it will take for these consequences to develop. So I don't have an answer to the second part of that question.
Aurora Cabela Viviani says, in the simulations, did you take into account irrigation associated recharge as well as historical withdrawals?
In the ones for the Hawaii volcanic aquifer study, yes, we did. For the He'ia and Waihe'e simulations, we did not.
We still have time for a few more questions, so we'll keep it open. Tom Jambaluka says, great presentation, super interesting work. And I have a question about one of the slides that showed a map of recharge change as a result of rainfall change over time. It looked like there was a discontinuity at the Ko'olau summit. Why is that?
Okay, let's see if I can find that. Oh, there, this one. Discontinuity at the Ko'olau summit. Oh,
So, yeah.
right here.
Yes. Well, I guess those are aquifer boundaries, or yeah.
Yeah, actually, you know, you're right. We did, one of the things that we did for the model, the groundwater model recharge, was to change, to use different period for the recharge for the dike impounded groundwater than we did for other areas that were not dike impounded. And the reason was that we felt that the water that was in the, because of steady state, you know, we needed to represent the water that was probably, we needed to calibrate the model to the water that was probably affecting our calibration points, including our water levels and our stream-based flows. And so we did use a different recharge period for the dike impounded groundwater versus other areas. So yeah, I guess this would be, so because of that, we have this kind of artificial discontinuity between the two areas.
Got it. Thanks, Scott. This is really, really good and good to see you.
Yeah, good to see you too, Tom.
Okay, looks like several questions / comments came in the last minute, so I'm gonna read those out, but after Stephen Howell's comment, I'm gonna say that's the end of the Q&A. So first from Jonathan Scheuer, did I read your slide correctly that increased pumping in central Oahu Schofield could reduce inflows and presumably sustainable yield in Waianae?
I think you're talking about this one. No, okay, so the decrease in flows from, yeah, so this is the future withdrawal increase, and that causes a decrease in flow to the freshwater lenses. It's actually causing an increase in flow from the dike impounded groundwater in Waianae. So in that way, yes, there's less water going to be available in Waianae, according to the model, at least.
Okay. Aurora says, I was also wondering about the discontinuity and salinity around the Waianae Range dike impounded. Can you speak a little more about that result? It was in the first half of the talk.
Okay, discontinuity. Maybe.
Oh, yeah, this one.
Okay.
Yeah.
Yeah. So what do you want to, which discontinuity? This here?
Oh, yeah, it's really, the change in interface is really large around that central region. And I just,
Right here.
can you explain how that works or why?
Yeah, okay. So in the model, the this area probably in the pre-development, not pre-development, in the baseline scenario, probably was filled with fresh water. And so when you take water or reduce the amount of water here, then it's going to bring this the boundary inland, and that's why as a difference in what it was before, it's such a big difference. Did I say that right? That clear? It's you gotta, I think it helps if you think of it in 3 dimensions. So if you had a cross section here.
Yeah, I think agree. It would help to see a cross section to understand what's happening. So
Yeah.
thanks. So the biggest drop or the biggest changes are going to be around that sort of where the dike complex
yeah,
is.
let's see if I can explain it using this other figure that I had. Oh, this one. So yeah, so this is for Kauai, but let's say you have this dike impounded groundwater, and so this boundary, see how steep it is? All it has to do is move in a little bit, and you get this big change in the altitude of the freshwater saltwater boundary. So I think that's what we're seeing. That's why it's so stark in that area.
Thank you.
When it moves horizontally.
That makes sense.
Sorry, I was muted. Last one from Stephen. Looks like the timescales from your data are surprisingly short, just a few years at most. That's in the dike region. Do you expect other regions to respond as fast? That would be great news. Can verify the model quickly, not requiring decades to see whether the model works.
I'm guessing he means the question is referring to the Waihe'e and He'ia studies. That's where there's a time series like that. Is that so? This shows that the response is pretty fast, at least to withdrawals. So what? I'm sorry, I forgot the rest of the question.
Stephen, maybe I could unmute you and you can elaborate.
Okay, yeah, I was just surprised at how fast the base flow changed when you were changing the when you're withdrawing water from the wells and tunnels. It looks like it's almost instantaneous, or at least no more than a few years.
Yeah, okay.
Thinking that if that's true elsewhere, that's a good opportunity to verify your model.
Well, I think it is true here because of the proximity of the dike impounded groundwater to the stream. It may not be like, let's say if you were not in dike impounded groundwater, if you were at the Pearl Harbor aquifer and you increased withdrawal from that, and you were measuring discharge at the Pearl Harbor Springs, it might not be that instantaneous. But these are really close. Like here's the Haiku tunnel, and here's the gauge. And oh, sorry, I don't have a scale. But this is half a mile is maybe about half of the width of this this screen. So they're really close together. This whole drainage basin is 1 square mile. It's less than a square mile. So they're really close. So in this case, I think, yes, the response is pretty fast. But it's because of the proximity of the tunnel to the stream.
Okay. I saw another question.
Yeah. So
from Ali. Sorry, we're pretty over time, so I'm afraid we're gonna have to close up at this point. Yeah, once again, thank you, Scott, for joining our seminar series and for closing us out for the semester. And thank you all to everyone who've been joining us, not only in this semester, but I've seen a lot of names reappearing over the last couple of years. I'm glad to have you all here. And so, yeah, I'm gonna just turn it over to our director, Tom Jambaluka, to make any closing remarks, and then I'll let you all go to have a great summer.
Yeah, I just reiterate thanks to Scott for that really super interesting presentation and really amazing work. And this is a great way to kind of cap this semester's seminar series. Thanks, everyone. Please keep an eye out for our next seminar series coming up in the fall, and we'll see you then. Thanks.
Hey, thank you.
Thank you, everyone.